Hi everyone, welcome back to class. The first thing that we need to announce is that as a reminder, so assignment 2 we'll do next week. So basically before the start of the class in the next week. So take your time to finish assignment 2 here. So basically for the next week will be the deadline for assignment 2, and also for after the lecture for the next week we will actually upload assignment 3 on our course website. Okay, so for the class today, so let's continue to talk about divide and conquer algorithm. And today we will basically make a conclusion of a divide and conquer algorithm. So we will basically finish the discussion of integer multiplication, where we have started but have not finished the proof there. And also we will further talk about matrix multiplication. And after that, we will talk about a very important divide and conquer algorithm, the fast Fourier transform, and also correspondingly convolutions. So I think basically for the second half of the day, we will actually begin to talk about another type of algorithm, basically dynamic programming. And maybe we will depends on the process today, we will actually talk about the problem of weighted interval scheduling. So basically in greedy algorithm, we have been talking about the problem of interval scheduling, but I think actually we can use more algorithmic ideas to give actually an algorithm for a more general case. Okay, so let's start it. So basically, last time we talked about this case for integer multiplication. So for integer multiplication, I guess if we want to talk about the divide and conquer algorithm, and basically if you want to consider such kind of strategy, a very natural way, I mean, to make the divide here, basically the division here is that we cut the integers that you are given to me, that basically we have A and B here. So it is very natural that we consider an A here where actually we divided in the middle, that basically there are like n over 2 bit for A1 here, and also n over 2 a bit for A0 here. So basically, if we cut basically this A in the middle, so this is basically how we are actually cutting to the two numbers. Basically, we make such kind of cut, and basically we have A and B here. So in terms of the binary representations, we basically have this A equals to 2 to the n over 2 times A1 plus A0. And also for B here, it equals to 2 to the n over 2 times B1 plus B0. So I think this is quite straightforward. And the next thing that we talk about basically in the last hour of last class is that we consider multiplication between A and B here, but actually a good strategy that maybe you want to think about. So like in a naive way that we want to make the divide and conquer. So basically if there are like 4 multiplications between these A0, A1, B0, and B1, then basically this does not help us, and the corresponding cause is still n squared. But here, basically proposed by Karasuba, so we briefly mentioned, is that we can consider instead of, for the middle term, instead of we consider this A1 times B0 plus A0 times B1, we can make make a change on this. So basically we can consider this. So basically this part is equivalent to actually A1 plus A0 times B1 plus B0, and minus A1 B1 minus A0 B0. But A1 B1 and A0 and B0, they are basically we have acquired them from the other two parts. So this is basically quite good, and in general, as we discussed, is that actually to multiply two n-digit integers suffices that we multiply three integers, roughly speaking, of n over 2 digits, and basically we got this recursion. But actually for our convenience, it suffices that, I mean, maybe we can assume that n is like a power of 2, and it suffices that we have a good understanding about such kind of recursions. So basically, beginning for the class today, I'm going to show that as long as you have a recursion where t of n is smaller than 3 times t of n over 2 plus O of n, we are actually going to have this kind of relationship, that basically t of n is actually O of n to the log 2 of 3 here. Okay, so let's get started. So this is basically a very quick recap about what we talked about last time. So speaking of this recursion, I think we need to think about this. So recall that basically for instance, recall that basically in the case where, for instance, t of n goes to 4 times n over 2 plus O of n. So this is like the naive version. So this is the naive version we presented last time. So the thing that we did is that basically we consider something like t of n over n squared. This is equal to t of n over 2 divided by n over 2 squared. Maybe let me actually write a little bit larger here. So t of n divided by n squared equals to t of n over 2 divided by n over 2 squared plus O of 1 over n. And based on this, we finally get like T of n equals to O n squared. But this is actually not so interesting because this is just the same as you just like multiply two integers directly. So here we have another relationship where actually T of n equals to 3 times T of n over 2 plus O n. So maybe you want to think about maybe here, for instance, am I actually dividing something here? But actually you see that maybe if I divide n here, and this becomes like n over 3. But this is not, I mean, I think the correct English word here is homogeneous. So this is not as homogeneous as the original formula. So, I mean, maybe for instance, here you want to divide like n squared. But this also looks a little bit weird. I mean, here I think it is very interesting that after we have like for this 4 times T of n over 2, and actually we divide like n squared. So basically have an n here and n squared here, and like n over 2 here, but also similar n over 2 here. So this is really like somehow like a homogeneous formula. Here, I mean, for this current case, I mean, T of n equals to 3 times T of n over 2. I mean, I think in principle, I mean, if you have like a good understanding, you can utilize such kind of trick. But actually, I have to say that this is not as transparent as, I mean, as the case where here is like 4 times T of n over 2, or maybe like 2 times T of n over 2, where we have been using for a lot of times, and actually the recursive formula equals to O of n log n here. So here, I guess I'm actually showing something a little bit different. I mean, basically how to compute this. So basically we need to understand this. So any questions? Okay, so, oh, excuse me, I think this. Okay, so I guess maybe we need, I mean, I won't say it's like a better strategy, but at least we need another strategy for this. So basically, let's think about how we, the most direct way that we can do this. The most direct way. I mean, looking at such kind of recursive formula, you have like a function of n, I mean, T of n, and then you get something like T of n over 2. So it's just like, maybe you just like think about a really direct calculation. Oh, excuse me. A direct calculation. What will it give to you? So basically now you have like a T of n here. And you have this recursion. So you have T of n, and basically it gives you 3 of T of n over 2. So basically you have like a T of n over 2, T of n over 2, T of n over 2 here. And basically you have a cos of n here. And basically for the second layer, so now you have 3 copies of T of n over 2. So basically you now have like 3 times n over 2 here. So you just imagine that how you're actually doing this recursively. And now, I mean, for the next layer, you're going to have the 9 copies of T of n over 4, etc. And now it is actually going to give you like 3 squared times n over 4, etc. So this is just like actually by direct calculation. I mean, you have T of n equals to 3 times T of 2 plus O n. Then basically, you just do this further. You just do this, I mean, by doing this. So you have like an n here. And basically, you have like a 3 times n over 2 here. And basically, 3 squared times n over 4 here. So you know that mathematically, I mean, for our convenience, we just write this as like a large constant c times n here. So that is basically giving you a c times like a summation of k from 0 to log 2 of n here. I mean, the upper part of the summation is log 2 of n here because you just imagine this recursions. It has basically log 2n layers. So that is basically the summation range. And actually what you are having here is basically n times 3 over 2 to the k here. So we can just like put all these parts together. So in other words, this is basically n times 3 over 2. And basically, you look at this. This is just like n times 3 over 2 squared, etc. And that is the reason why actually you just like do a direct calculation here. I mean, from this recursive formula. And I think ultimately, you are going to get like a capital C times the summation here. So is this clear to you, or do you have any question? Okay, I think this is relatively straightforward. And I think the remaining thing is that after we have this kind of direct calculation, I mean, we have this summation here. What is this value? So this is basically what we need to take care of. So this is basically, as you can clearly see, it is a geometric series. I mean, you have like m plus like n times like 3 over 2, etc. But actually, nevertheless, you can just write this as like C of n times the summation of k equals to 0 from k equals to 0 to k equals to log 2n, and have this 3 over 2 times to the k here. So this is basically a geometric series. And actually, it is known that 1 plus q squared plus, let's say, q of m here. Let's not get confused here. And actually, this equals to 1 minus q to the m plus 1 over 1 minus q. Or I mean, this is typically the case where q is smaller than 1. But of course, you can like just like shift both the shift a minus sign both for the numerator and also the denominator, and actually you can get this. I mean, they're the same. So this is there's just no difference. I guess it is also very direct to just check this by calculation. I mean, if you have this 1 plus q squared plus q to the m times 1 minus q. I mean, this just gives you like a 1 plus q squared plus plus q to the m. And you minus the other things. I mean, the things you are minus here is that you have this q here, and you time it to this 1, this q squared, etc. And actually, the thing that you're going to minus is you just follow this, and you are going to have minus q squared minus minus q to the plus 1. And I guess it is clear that this just equals to 1 minus q to the m plus 1. So I guess this should be straightforward. So. Okay, so this is just like a very quick calculation about how the geometric series are how the values are going to take place. So basically, we have this formula here, and basically we want to take a look at what this value is. So you can clearly see that this is now going to equal to Cm times the ratio here, the q here is basically 3 over 2 here. So basically, you plug this 3 over 2 into this. You're going to have like this equals to 3 over 2 to the log 2n plus 1. Minus 1 divided by 3 over 2 minus 1. Is this clear to you? Okay, so let me actually draw like a row here. So maybe do this. So actually, this gives you that T of n equals to, let me just copy this, Cn times 3 over 2 to the log 2n plus 1 minus 1 divided by 3 over 2 here. But actually 3 over 2 here, this is not so, minus 1 here. So the 3 over 2 minus 1 is basically a half. And basically this is going to give you 2Cn times 2 log 2 of n plus 1 minus 1. So it is basically giving you this. And I guess we can just basically write everything down here. So we have a plus 1 here. So this is not looking that direct. So maybe we can write like this. So basically it is 3 over 2 to the log 2n times another 3 over 2 minus 1 here. So this is just going to equal to 3Cn times 3 over 2 up to n. So basically it is this part. We just like multiply the 3 over 2 with this 2Cn here. And basically we get 3Cn here. And basically for the minus 1, we are going to minus 2Cn. So, I mean, I guess this is probably not as elegant as like using this. I mean, this is really like a clever observation. I mean, if you have like such kind of form, I mean, if it's like a 4 or this is like a 2 here, we have the way to make this like a homogeneous formula and basically directly see what Tn's are. But nevertheless, I mean, in general, I mean, we can write like a whatever recursive formula, basically in this kind of form. You can always do this kind of direct calculation. Basically, it should, in general, should be this kind of geometric series, and you can make this calculation. And basically, we get this. So the only remaining thing is that we need to understand what this is. I mean, in general, I mean, if you maybe for instance, you have like in your assignment, maybe in your final exam, you can write this kind of form, but this is, I mean, typically we write like polynomials, and hopefully, and this is still like a polynomial in terms of n, and that would be great. And in general, I expect that everyone should have an understanding about how to turn this into a closed form of polynomials. So basically, let's see how this is going to work. So like a quick recap about some very basic math formula is that the E here equals to the limitation. I mean, I might have mentioned this not this for the first time, but I guess it's just a quick recap about basic knowledge in calculus. So recall E equals to this limitation, and it is in general known that a value A here equals to E to the ln A. So the ln here is just that defined as log E of A here. And actually, it is also known that log A of B equals to ln B divided by ln A. So I guess this should be relatively straightforward. And I guess the only remaining thing is that we need to have a good understanding about what this is. I mean, basically 3/2 to the log 2n here. So we actually have this. So 3/2 to the log 2n. I mean, we really need to make this, I mean, this is like a log 2n here, but in general, I mean, the logarithm with E as the basis, basically this ln, I mean, this is more flexible. So this is the first step we are going to do here is that 3/2 to the log 2 of n here. We can clearly see that this equals to E to the ln 3/2 to the log 2 of n. I mean, actually, we can make a further step that instead of writing this log 2n here, we can write this as ln n over ln 2. Is this clear to you? So basically, this log 2n, I mean, we just like use this. It's just equals to ln n over ln 2 here. So what is this? So we can just like recap everything here. I mean, for things in the exponent, I mean, it is basically equals to E to the ln 3/2 times ln n divided by ln 2 here. So it's basically an exponent like this. But we can actually make a rearrangement like this. And basically, I mean, we have the E here and we have the ln n here. And this is basically what we want. And basically, we can rewrite this as E to the ln n to the ln 3/2 divided by ln 2. And this is actually going to give, because E to the ln n, this is, I think this is very straightforward. This just equals to n. And then we basically, I mean, this is like a ln 3/2 divided by ln 2. And we can just actually use this formula. And then basically this gives you n to the log 2 of 3/2. So is this clear to you? Do you have any questions? Is my writing large enough? Shall I actually? Sure, sure. I think I will try to write a little bit larger because indeed the numbers here are a little bit small. Maybe let me actually freeze here for 1 or 2 minutes. And I can further think about this. Okay. Okay. Okay, so the conclusion we are currently having is that T of n, then it equals to 3n times n to the log 2, 3/2 minus 2n. I mean, I probably omitted the c here, so that. write a C here. So this is basically the formula we are currently having here. And actually, we can make a further combination that is equals to 3c times n to the log 3 over 2 plus 1 minus 2cn here. So actually, there is another formula that in general, I mean, for like a whatever, I mean, let me use the red color here. So for whatever base, I mean, like log C of AB equals to log CA plus log C. This is also a well-known formula that we know for logarithms. So actually here we can actually combine this one and actually this log 2 of 3 over 2 together. I mean, we just consider like this. 1 equals to log 2, 2. Let me actually write this a little bit larger. So 1 here equals to log 2, 2 here minus 2cn. And that is basically a reason, I mean, we just combine these two together. We have a log 2 of 3 over 2 and also a log 2, 2 here. So this just equals to 3c times n to the log n, log 2, 3 minus c. So here we know that log 2, 3, I mean, this is actually a larger than 1. And of course, on the other hand, it is smaller than 2. This is just because, I mean, 3 is between 2 and 4 because 3 is actually larger than 2 to the 1 and actually smaller than 2 to the 2. So basically, we know that log 2, 3 is actually larger than 1 and smaller than 2. So because log 2, 3 is larger than 1 here, so this term you are minus here. I mean, you minus like a linear term in m. But actually, the previous term, I mean, this term, it is actually the exponent in terms of n is larger than 1. So this is basically the second term. I mean, this linear term is actually going to be omitted. And actually, because the C here is also something we can contain in the big O notation. So this just equals to n to the log 2, 3. And basically, as we mentioned, I mean, there can be like a calculation to actually specify the detailed value of this log 2, 3 here. So this roughly speaking is to 1.585. And basically, this finally gives you like T of n equals to O of n to the 1.585. Okay, so any questions about like this calculation? So in general, you can clearly see that, I mean, for such kind of formula, I mean, for the, as I just mentioned, for here, if you have like a 4 here, maybe you have a 2 here, then basically you can have like a clear observation to directly give you a formula. But nevertheless, I mean, for instance, here in this Karlsruhe recursion, basically this is probably not so transparent, but you can still make a detailed calculation basically based on geometric series and based on some calculation about like the specific logarithmic term that you're actually having here. So basically, you can finally make the conclusion that basically the cost of this Karlsruhe algorithm is going to be, in general, like n to the log 2, 3, and basically this is like bounded by this value. Okay, so any questions? Okay. So that basically, I mean, maybe let me just write this again. So conclusion. So this is very firstly proposed by Karlsruhe and also Hoffman. And basically we can multiply the two n-digit integers. Basically in this O of n to the 1.585 beta operations. Okay, so basically this gives you the answer to the problem integer multiplication. So the next question maybe that we want to think about is matrix multiplication. So for the matrix multiplication problem, it is basically a very natural generalization of the integer multiplication problem. So here we have two n by n matrices, A and B, and we want to compute C equals to A times B here. So in terms of linear algebra, this is basically something like this. So we have like a matrix A here, which actually actually equals to like A11, A12 until A1n here, be A21, A22, and N1, AN2, ANN, times like another B here. So maybe let me just also write this down. The C here, basically, we need to compute this multiplication. This C is basically another n by n matrix. C2n. C. So this matrix multiplication problem is just so ubiquitous. I mean, just like so common in computer science. I mean, in mathematics, basically. In general, in applied, I mean, basically any area that is related to applied mathematics. I mean, even like, for instance, you work in AI, maybe, for instance, in computer vision, or maybe, for instance, natural language processing sector, you just need to like multiply integers and multiply matrices. And this is just like in general, so common. I mean, and that is the reason why we actually want to have a very good understanding about like what is like the limit. I mean, what is the best possible algorithm that we can give for integer multiplication and also matrix multiplication problems. Okay, so just imagine the brute force. I mean, the brute force, I probably won't even say this is like an algorithm, but you just like compute, I mean, compute the multiplication of this row and this column, the same row and this column, and the same row and this column, and then you go to like the next row and the next column, etc. I mean, you can just do this. I mean, there are basically in general n rows in A, n columns in B, and each multiplication takes O(n) cost. Because if you multiply each row and each column, you actually make n multiplications. So basically each multiplication is going to take O of n cost. So this just suggests that the brute force algorithm is going to give like O of n for the three arithmetic operations. Okay. I mean, in general, you think about like problems. I mean, matrix multiplication problems that maybe you're going to happen in the real case. I mean, for instance, maybe this n is like a million. I mean, 10 to the 6. I mean, if n equals to 10 to the 6, I mean, in general, this scales like 10 to the 18. I mean, this really sounds quite bad. This is probably not so helpful. But even if, for instance, you can improve like a factor of n here, or maybe that is too significant. But for instance, say if you can improve the square root of n, that is basically you're improving a factor of 1,000. So basically, such kind of improvement is very important. I mean, for a problem like integer multiplication or matrix multiplication, etc. You really want to have like as good exponent here as possible. And actually, this is I mean, following the discussion of divide and conquer, as you can directly imagine, this is also something we want to have a good understanding about here. So I guess we are actually quite motivated by integer multiplication because the matrix multiplication is a direct generalization of the integer multiplication problem. So maybe we can consider like a further improvement, like can we improve upon this? On this. So here we are very naturally, we are going to continue to use the divide and conquer idea. And basically a divide here is basically that we want to partition A and B. I mean, here the partition, I mean, for integer, you just cut in the middle and you have two pieces. And maybe you want to consider like sizes of n over 2. So here, if you want to cut this, maybe you are going to now, because a matrix is like a two-dimensional thing. After you're making this cut, it's actually going to give you 4 pieces, and each piece of dimension n over 2 by n over 2 here. So a direct conquer is actually going to give you like multiplication of 8 n over 2, n over 2 of n over 2 pieces. So what do I mean by that? So in general, just consider, the division I'm describing here is that maybe you have an A here, maybe you have a B here. The A here, you can regard this as like A11, A12, A21, A22 here. And also the B here, you can regard it as a B11, B12, B21, and B22 here. So each of the A's and B's, they are block matrices, and each of that's n over 2 by n over 2 here. So the C here is basically, we can also regard this as a block matrix. Like goes to this. So why we are saying that we are multiply 8 n over 2 by n over 2 matrices, it's just like consider this. So basically this gives you 2 multiplications, and this gives you another 2. And this gives you another 2. And this gives you another 2. So that is basically in total a 4 matrix multiplications. And basically after that, of course, we need to combine the outputs. We just like the appropriate. Okay. So as you can imagine, this is actually going to give you a formula, something like T of n equals to 8 times n over 2 plus like O of n squared. Because here you're actually adding matrices. I mean, if you want to add like an n over 2 by n over 2 matrix, the cost of adding here is basically n squared over 4. So basically this part, I mean, if you add like, you want to consider a matrix addition, that basically this part of cost is O of n squared. And in general, this cost of this recursive formula, I mean, here because you have 8 multiplication here. So that is why we have T of n equals to 8 times T of n over 2 plus O n squared here. So basically this is still like a naive way that we can do this. And actually, maybe let me omit the technical details, but you can imagine that, I mean, doing the divide and conquer in a naive way will only give you an answer in a naive sense. Basically, you can make a calculation offhand. And actually, if you have like an 8 here, so this is something not so difficult. You can just like, consider this. You consider divided by n cube for both hands. So this equals to t of n divided by n cube, and this equals to t of n squared divided by this. Plus like O of 1 over n. And it is not difficult to see that this is basically suggesting that T of n just equals to O n cube. And actually, I mean, basically as what I was saying just now, like a divide and conquer in a naive sense, we will just give you a naive error. So any questions? Okay, so I guess we are talking about some interesting algorithms. I guess you are probably not going to get satisfied get satisfactory if I only mention such kind of like naive algorithms. So a key observation here, I mean, is that basically similar to Karasuba. I mean, actually, there are some clever observation here. So actually multiply 2 by 2 block matrices can actually be finished by 7 multiplications. So how is this achieved? So basically there are, I mean, there are some calculations here. I guess I will probably just write this down. I mean, we basically still have this. I mean, in general, we can consider such kind of pieces. I mean, basically we consider a piece called P1. P1 equals to this. Two equals to this. I mean, I have to say this is actually much more complicated. And basically, I think I guess the idea of Karatsuba should be relatively straightforward, and I think I strongly suggest you to remember the formula. I mean, basically how Karatsuba make this kind of change. But I think for this, I mean, I should call this like this is known as Tarassen's algorithm. You are not required to remember the details of Tarassen's algorithm because this is really something a little bit contrived. I mean, there are some attempts, and basically, maybe you can run some like programs to check what this is, and basically whether you are actually going to give you like a correct form along this. Say two. And actually, after having these 7 pieces, I mean P1, P2, P3 until P7, then actually you can also make a check that C11 equals to P5 plus P4 minus P2 plus P6. Yes. So I would like to emphasize, as I just mentioned, I mean, this is not required for, I mean, you don't have to remember these complicated formulas. It's just like to show you actually how this is possible. I mean, it's not required to remember, but just to show how this is actually a possible way. And actually on this, you can clearly see because we only have 7 pieces here. And basically for all the 7 pieces, we have these multiplications. And the other parts, I mean, for the C's here is basically additions. So with some calculations, you can see that this is basically 7 multiplications. Actually 18 additions. And I guess similar to the Karatsuba algorithm, you can see that this actually gives you a formula basically like T of n equals to 7 times T of n over 2 plus O(n) squared. So basically, this is like a homework problem. I mean, you can check this. You can check this offline. But I guess from the beauty of mathematics, I mean, for instance, from the Karatsuba algorithm here. So, so for the Karatsuba algorithm here, we basically have this T of n is like 3 times T of n over 2 plus O(n). And we get this result. The exponent is log 2 of 3 here. So basically, you can check this offline, but T of n here equals to O of n to the log 2 of 7. So this is basically you can follow a basically totally similar pattern. I mean, you just do this. I mean, you just compute this direct calculation. You have like a good calculation in the geometric series, and you are going to figure out what is the exact value here. So basically, T of n here equals to n to the log 2 of 7, and this is basically equals to n O of n to the 2.81. And this is actually, as I just mentioned, proposed by Strassen in 1916. Okay, so any questions? Okay, so I think basically last class, some student asked me, I mean, whether this Karatsuba algorithm, or maybe here for the Strassen's algorithm for matrix multiplication, it is practical or not. So I would like to mention a few further points about this. So there are definitely some implementation issues of Strassen's algorithm. So for Strassen's algorithm, we definitely need like a larger cache. So basically I mean, if you consider like direct matrix multiplication, I mean, you just like put A here, you put a B here. I mean, you just like multiply the rows and columns. But for Strasson's algorithm, you basically need to have space to store all this P1 to P7. And this can be a little bit cumbersome. Basically, you need like a computer with a decent size of cache. And I think the other point is that how to utilize sparsity. So actually, in a lot of engineering problems, you are not like having like a huge matrix A and B here. I mean, all these entries, they are non-zero. I mean, in the worst case, of course, it can be, but actually for a lot of problems, for instance, in recommendation systems. So in recommendation system, typically we have like a low rank matrix. Or maybe we have, typically for a lot of problems, we have other structures to utilize. I mean, maybe it is sparse, that like the total number, I mean, there are a lot of zeros actually in the matrix. But as you can see that for a Strasson's algorithm, in general for divide and conquer, you are not going to utilize this kind of structure because we're making the division here. Maybe if you have the rank, even if you have the low rankness, or maybe you have sparsity, some of the elements, they are non-zero, they're actually, a lot of them are actually zero. But this is not so helpful for Strasson's algorithm. Maybe actually you can see for engineering-based methods, if you have some kind of specific structure, there are actually a very good algorithm that you can utilize. And I think the other thing is numerical stability. Because such kind of calculations, I mean, from P1 to P7, you also need to combine everything together. So this is typically a little bit cumbersome. I mean, speaking of like the stability of the algorithm, it is definitely not as good as the regional algorithm. I mean, just like do the brute force way. But I think there are, nevertheless, there are also some other points I would like to mention. So this is basically like a remark. So a remark here that I think I will also, on the other hand, explain that it is a misconception. That Strasson's algorithm is only of theoretical curiosity. So Strasson's algorithm, I mean, there are also, as I will discuss in a minute, there are also other, I mean, more advanced matrix multiplication algorithm, and actually many more advanced algorithms, they are really, from at least from my perspective, only of theoretical curiosity. But Strasson's algorithm, I mean, compared to more advanced algorithm, it enjoys like a relatively simple structure. So actually, there are some advanced numerical studies. So for instance, advanced computation at Apple. I mean, in general, for a lot of companies, they have the group of HPC, high performance computing. So actually, people really want to test algorithm. I mean, for instance, like Strasson's algorithm, maybe like the brute force way, and maybe a more advanced algorithm. So there are numerical evidence that Strasson's algorithm can perform well. So for instance, like reports, like for instance, like approximately 8 times a speed up. When n is basically not so small, so when n is basically like maybe like 2,000 to 3,000. But nevertheless, I mean, this is probably definitely if you consider such kind of multiplication, it depends on like the structure of the matrices. I mean, if you for like huge, I mean, dense matrices, for the worst case, I mean, you can imagine that Strasson's algorithm should be better than the brute force. But this is definitely very arguable. I mean, the range of instances where it's useful is a subject of controversy. So the second point is that, I mean, due to the time limitation, we probably, I mean, we also probably don't want to like stick with such kind of like integer multiplication, matrix multiplication for a long time. But I just want to mention that it is possible that we can basically use the same idea to solve other linear algebraic problems. So it is possible, I mean, to Strassonize, for instance, like linear system solving. Maybe, for instance, like computing like determinant of a matrix. Maybe, for instance, like eigenvalues and others. So in general, for a lot of, linear algebraic problems, you have this kind of divide and conquer ideas inside, and basically you can use something similar to the Strasson's algorithm to get correspondingly faster algorithms. So the third point. So this part, for the Strasson's algorithm, we consider like multiplication between like this kind of n over 2 by n over 2 blocks. Using 7 multiplications. This formula is, I have to say, is probably not so beautiful. But in general, people also, from a research perspective, also think about like further restrictions. If you can make like this to be like 7 multiplications, is it further possible to make this to be, for instance, like 6 multiplications? So it is actually shown in a research paper that it's impossible to actually multiply two 2 by 2 matrices. With only 6 scalar multiple, because we are talking about like 2 by 2 matrices, then it becomes to scalar multiplications. This is also a relatively old result. This is an old result by Hopcroft. Sure. In like 50 years ago. So if this were possible, n to the log 6, this equals to O of n to the log 2.59 here. So this is apparently smaller than a Strasson's bound, which is roughly speaking like n to the 2.81 here. But this is just impossible by using the divide and conquer idea. So maybe you want to, this is something can be a little bit contrived. Maybe you want to further think about whether this is possible. You want to maybe go to a little bit larger matrices and actually whether this is possible. But actually it is impossible to multiply 3 by 3 matrices with only, the value here is 22. So this is actually not possible. Scalar multiplication. So this is impossible. If you have like two 3 by 3 matrices, and actually you only have like 21 scalar multiplications, actually you cannot make this. So actually looking at this equals to O of n log 3 of 21. And this actually equals to O of n to the 2.77. And we can clearly see, if you actually go a little bit larger, for instance, you can just consider 3 by 3 matrices. The thing that you can do is actually not far from Strasson. And on the other hand, for Strasson's algorithm, you can actually consider, relatively simple matrices. We only consider 2 by 2 matrices. So this also suggests that basically Strasson's algorithm is something pretty good among the class of using divide and conquer to solve the matrix multiplication problem. So the fourth remark that we are going to make is that using more advanced techniques, I guess, we are talking about theoretical results, so let me definitely mention some good theoretical results. So best known results. Fast matrix multiplication. So basically, in 1987, there's a very significant breakthrough result that can show this can be solved into the 2.376 by Copperschmidt and Vinograd. In 1987. So the state of the art compared to this is basically into the 2.37286. This is the current state of the art by Ellman and Williams. In the SOTA conference last year. I mean, you can clearly see that Strasson's algorithm is a significant improvement compared to the naive way. And actually, Cooper-Schmidt and Winograd, at least from a theoretical perspective, is like a significant improvement compared to Strasson's algorithm. Like recently, I mean, development, there are some improvements, but they are relatively insignificant. I mean, let me wrap up in another minute. So basically, those algorithms are purely theoretical. I mean, actually, in some libraries, people use Strasson's algorithm, but like for Cooper-Schmidt and Winograd, I mean, this is probably really something from a theoretical perspective, and because the constant in the big O notation, they are so large. I mean, this is probably not so helpful, but it is interesting at least to know there are some such kind of theoretical results. And basically, I mean, after discussing this, I guess we finished the part of integer and matrix multiplications. So if you don't have any questions, then we can just like take a break and let's come back in 10 minutes.